December 13th, 2019. Theoretical physics. Some new ideas and some old information about the abundances of the various chemical elements. And as I tell you about the new ideas, I'm going to talk about lithium being quite rare, but that's because iron is common. Now, in the new idea I'm presenting, it's a static nucleus theory, so that makes it a little easier to analyze than in other theoretical physics about the nuclear structure, where it's quarks and gluons. The static nucleus theory is spheres that are stacking into simple cubic lattice in the core of the nucleus. And the six faces of the cube get some pile of protons and neutrons that armor it against collisions. And 62 of the elements in the periodic table are using lithium-5 as part. So what I'm going to be talking about is, of course, the periodic table of nuclear structure, which I have provided, and you can get your own copy of it, or you could find one which Standard Science is trying to provide, although they only have like 4 elements filled in on this chart as little pear shapes and fuzzy, foggy areas. So you can get yours at pyramidalcube.blogspot.com. And then you can check out what it is that has these shapes in there, like little snowflakes. Each one's different. Each element is different. And one thing you find is that there's an even-odd difference for Z. A Z is the number of protons in an element. So let's just talk about this quietly for a couple of minutes here. Hello, my name's Alan Folmsby, and today I am streaming live on YouTube, and the thing is that the abundances of the various chemical elements is charted on the internet, and you can go look it up yourself in places. So actually it's copyrighted there. So I'm going to have to draw a picture myself of something that's not copyrighted, so that you can then see about the abundances of the different elements. And I'm going to show you a graph on paper. On the left side is going to be like hydrogen, and on the right will be all the heavy elements like uranium and stuff. And we're going to rank them from left to right as the Z is increased from 1 through 118. And you'll see that the light elements are very common, except lithium is rare, element number 3. Why is that? And beryllium is rare. And then iron is very common. And you'll see as I draw this chart here coming up right after I turn the camera around towards a piece of paper. I'm turning the camera now while you're reading this nice thing. Okay, I hope this will focus once I start drawing the chart here. Well, that was nice. So the thing is that on the left side would be, say, hydrogen, and then iron would be over here, and then a common. Let's see, I can look at the copyrighted material myself, but I'm not allowed to show it to you. Let's see, barium is quite common at 56. So this is in the sun. And even if you get to much heavier things like mercury, number 80. And in the sun, the graph is going to be drawn in a couple seconds for you. All right, I think I'll get my nice pen going here again. All right, so here it is on the left. Hydrogen is very common, and then helium is common, and then lithium is very uncommon. And then it goes up and down quite a bit, so that even ones are common. So that even number Z elements are common at the top, like these. You can see these peaks here. Let's see what that is, where I just put a dot there. Oh, what do you know? That's iron, number 26. It's even. And then lithium is down here, and it's very rare. So you might wonder, like, why? Why is that? And other things are rare. Let's see, there's one down here, which is called fluorine. Now, in the static nucleus theory, there's an explanation for this. Here is oxygen, and I'm going to show you fluorine. Fluorine adds one more white proton onto this, making it unsymmetrical. So in other words, this is a symmetrical shape here. And by adding one more proton anywhere makes it unsymmetrical. So it's less survival qualities. And that's what this slide here is saying down at the bottom here. It says symmetry is a survival trait during collisions. So that oxygen survives well because the pyramidal cube structure is symmetrical. But fluorine doesn't survive a lot because it's not symmetrical, and it therefore can turn away from safety. It can become vulnerable by being torque being exerted on it. For example, if we look again at oxygen here, we could zoom in on the periodic table where this silhouette is shown, and you can obtain your own periodic table also. All right, there's oxygen up at the top right. You can see it's symmetrical from left to right, and if we rotate it 90 degrees, it's symmetrical on all four sides. So that's one of the rules of the pyramidal cube structure there. And if you add one more, then you get fluorine, which I'll show you coming up here. All right, there, fluorine next to neon. You can see it's not symmetrical. Neon is element 10, and you see left to right it's symmetrical. So it's much more common than fluorine. And on the left there you see fluorine has one blue dot for the incremental proton added on top of the foundation of oxygen. And during a collision situation, there could be a time when this off-center proton there exerts torque on it, so it rotates into a bad position for an incoming flux of collisions, whereas symmetrical ones would not be rotated, but would maintain whatever orientation had been a good survival trait in the first place. All right, so we could also look at, for example, iron, and next to it is cobalt, a very uncommon thing. So we see here iron, number 26, and next to it's cobalt, much lower on it. Let's see, it's like 1,000 times, no, not 1,000, let's see, 100 times less common than iron. And here's why. Here's the iron nucleus, and you can see the symmetrical shape here. so that it's a cube at the center with 3 layers, and then on the top there's a little pyramid like a lithium, and on the left there's a little pyramid over here on the left on top of the cube. That's lithium 5, and in fact there's 6 lithium 5s being consumed just to produce 1 iron. I speculate that is the reason why lithium is rare and iron is common. Now, if we added 1 more proton, it would be attached here for cobalt, and that makes it not symmetrical. And if we add 1 more for nickel on the other side, then it becomes symmetrical. And in fact, nickel is at least 12 times as common as cobalt because it's symmetrical. So nickel then would get 1 attached here on that point on the cube, and then nickel gets another one back here. So that balances it out, making it symmetrical. So over and over you get this throughout the entire periodic table. And as we see in the periodic table here, iron is in the middle there, and it is symmetrical. And you can see a close-up of it here. You see there's 27 baryons in the red cube and 30 baryons in the black pyramids. Baryons are protons and neutrons. And then cobalt, you see, has that blue dot, making it unsymmetrical. Nickel has 2 little blue dots. Oh, there it is. Nickel has 2 blue dots, so it's more symmetrical than cobalt. Now, this explains the abundances of the various chemical elements. Lithium gets consumed, and if you looked at some kind of the amount, I got to change my camera angle here. So if you change this lac right here, all this missing for lithium, beryllium, all that area missing, the abundance of those protons and neutrons is put on top of all the ones that are more abundant. All these peaks that are sticking up here contain a lithium 5 on the cap. And I'm going to tell you a little about this here for the, let's see, I have to move forward here. Now, oh, there's a good close-up of the periodic table. Notice that iron has those little triangles. That's lithium 5, the black triangles. And almost every element has a peak on top of the cube. And those are lithiums that were scattered away from the star, and it just got attached to the heavier elements. And that's why the common even elements have taken away the lithium and beryllium out of the stars and consumed them to fuse into heavier things. So you can get a copy of this periodic table of nuclear structure at the impuremath.wordpress.com website. And then I'm going to go back to the hand-drawn thing, and we're going to talk about the abundance in the earth. Okay, on my right, where you can't see it, I have copyrighted standard science material, which I'm not allowed to show you. But I'm going to draw in how the Earth numbers are. See, hydrogen starts out much lower in the Earth, but oxygen is also high again. Let's say right here, being oxygen is very common on the Earth. And then the other elements that are way up there is silicon as a peak, A very low one is argon, a low point. And in fact, all of the gases, all the rare noble gases are quite rare. And then when we get to iron, that's very abundant also. So this graph looks very different than the other one for the sun. And there's not as much variation. There's about 100 times as much variation in the sun, abundances of elements, as there are variation amongst the elements in the crust of the Earth. So that's what I'm trying to show here. Let me tear this off, and then we'll talk about the abundance in the Earth. It looks like this, what I'm looking at on the copyrighted material. All right, there it is. See, there's not much variation, and these numbers are just 100 times smaller range than in the sun. So instead of being over a factor of 1 billion in abundance between the rare and the common, this one is only a factor. Let's see. It looks like it's not as bad as I thought. But anyway, maybe it's only less than 100 times different. But anyway, the thing is that, let me check out which ones are even. Let's see, there's iron's even, is very common. Calcium is even. And even in the Earth's crust, if we look at the ones that are common, silicon is even. Oxygen is even. And if we go to heavy elements, we see strontium is one of these peaks out here. And then another peak way out is barium, another very even Z. And then towards the heavy things, we see lead, number 82, is a heavy one, very common element, even. Even in the Earth's crust, thorium, number 90, is even. I didn't see any common ones. What about phosphorus? Let's see where phosphorus is here. Oh, there it is. It's medium commonality. It looks like it's over here. Phosphorus, kind of a medium there. And it is odd. So it's not the most abundant there. So this kind of checking into the abundances of the elements is partly to confirm the correctness of the pyramidal cube theory of nuclear structure. And the part of this is about the technetium and promethium. The abundances of these elements is almost zero. I mean, on these charts here, you know, element 43, they don't even list it. It's just a blank on the standard science. That's zero. Oh, I know why. It's less than 10 to the minus 9th abundance, so that's way off the charts on the bottom. And the same with promethium. And here's the new information I'm giving you today. These cube 4 elements of technetium and promethium are unstable because the center is a void. The cube 3 elements like iron are stable because the center of the cube is a neutron or proton. The light elements with the cube 2 at the center are stable because there's only one layer of nucleons above the void at the center. So write it down. Memorize that along with the gravity volume theory formula, and you'll be able to use it in the future. All right, so as we see, your technetium at the bottom of the picture has a cube at the center with 4 layers. So at the center of that red square is a void. Whereas in iron, you see there, at the center of the red square of red baryons, is a baryon. There's no void at the center of iron, so it's stable. Technetium, and then promethium also has the same kind of Q4 as technetium there. It's right below technetium in the periodic table. As you could see here, near the center left, you can see technetium and promethium right above each other. And I've rearranged the periodic table now so that the lanthanides and actinides are put back in instead of being taken out. Now, one comment I would like to make is about why there are 8 elements in the second row of the periodic table, 8 elements in the third row. Those are periods. The columns are groups. And but in the fourth row, we see there's 18 elements. What does 18 have to do with anything? Well, the octet rule. So, hey, let's talk about the octet rule, because it also has an 18 rule and a 32 rule. You notice in the period 6 and 7 of the periodic table, there's 32 elements in each row, each period. And then above that, in period 5, there's 18. So, and here I'm going to explain why that is according to the pyramidal cube theory. All right, 8 is equal to 6 plus 2. That's where the octet rule comes from. The cube has 6 faces, and so they get covered with 6 protons, or piles of protons that have a tip of 3 protons. But for the light elements, it's simply the 2 in the center cube plus the 6 faces. Makes the 8 for the octet rule. And the 2 in the center here, the cube has 2 protons in it, just like in chemistry. There's 2 electrons in the inner s orbital. All right, 18. Where does that come from? That is 6 times 3. There's 6 faces on the cube, and each face is covered with a pyramid of nucleons with a tip having 3 protons. So as we see in this here, there's a lot of heavier elements in the 4th and 5th row that have tips on the pyramids with 3. And so that's where 18 comes from. All right, then 32 is explained as follows. It's the 18 from the tips of the 6 pyramids plus the 14 in the cube. And that's where you have a 3-layer cube. Of course, 3 cubes is 27. And if there are a checkerboard pattern of protons and neutrons in there, then you get half them are protons and half are neutrons. So half of 27 is 13 and a half. So there can be 14 protons in the cube, or there could be 13 in the cube, depending on how the choice is made. So using 14, adding that to the 18 on the tips gives 32. And that explains that. And the tips of these can be seen in this periodic table here. So I'm just about done with the abundances of the elements. Now here's one last picture of from the silhouettes of the nucleus. Polonium and radon are shown here. And they are radioactive. And they have a geometric reason for being radioactive. The polonium there on the left, you see, will decay because the bottom pyramid protrudes away. And it's a directional type of a nucleus where collisions will tear away at that bottom edge there, the four-layer black pyramid there, where black is protons and neutrons in a hexagonal close pack, and the red is protons and neutrons in a simple cubic lattice. Now the element on the right is radon, and that is radioactive, and it decays in like 4 days because those pyramids on the left and right are large, and they're protruding away out from the armoring protection of the upper massive pyramid of this pear-shaped element. All right, now I'm just about done for now, but I'm just going to turn the camera around here briefly. All right, so that's the end of the presentation for today. Thanks a lot. This is Alan Folmsby from Maui and this live streaming webcast. And I'll be back every Monday, Wednesday, and Friday at the same time, 20 hours Greenwich Mean Time.